Alrighty, welcome to the acids and bases unit. For this video, we're going to introduce what acids and bases are and the pH scale here. Before we get into the notes here, there's a list of all the terms that you should know from this unit, which we will go through as we progress through the lessons. To start off with acids and bases, all matter is classified as either an acid, base, or a neutral compound. So neutral just means that whatever you're talking about has a pH of 7 exactly on the pH scale. If it's 7.01 or 6.99, it's not neutral. It's close to neutral, but neutral means exactly 7 on the pH scale. Okay, and what the pH scale does is it just measures the acidity of a compound. So on this line right here, this is going to be where our pH scale is. So right in the middle, that's where 7 is going to be, and this is neutral. Now our pH scale goes up all the way to 14. And 14 is where we're going to have very basic substances. Okay, but anywhere above 7 or above a pH of 7 is going to be considered a base. Okay, 14 is just very basic. Meanwhile, on the other side here, our pH scale goes down to 0, and if you have a substance with a pH of 0, it's going to be very acidic. Okay, but in general, anything that has a pH lower than 7 is considered an acid. Now, just so that you know, pH just stands for power of hydrogen, and that's what a pH scale is measuring there, and that's what's connected to the acidity of a compound. Okay, so when you have an acidic substance, it's going to have a high concentration of H plus ions, or as we'll learn in the future, hydronium ions, which is H3O plus. So high concentration of H plus ions, which that is for the Arrhenius definition of an acid, which I'm going to abbreviate definition to just DEFN. Or eventually we'll start talking about the modified Arrhenius definition of acids and bases, which will expand to include hydronium ions, which is just this, H3O plus. So just so that you're aware, earlier on in our notes, we will focus on the original Arrhenius definition of acids and base, but we will move on to the modified definition, or the modified Arrhenius definition of acids and bases, just because it's a little bit more accurate. Moving over to the base side, bases typically have a low concentration of H plus ions or hydronium ions. So essentially, the higher the concentration of either H plus ions or hydronium ions, the more acidic something is going to be. Now, acids and bases, they're pretty prevalent in our everyday lives. So for example, in the body, saliva protects our teeth from acidic foods. Now, saliva typically has a pH anywhere between 6.2 and 7.6. It just kind of depends on what types of foods that you're eating. So if you're eating more acidic foods, then maybe the pH of your saliva is a little bit more on the acidic side of that range. Okay, meanwhile, stomach acids, that's going to be way more acidic than your saliva. So that's going to have a pH around 2. Okay, and sodium bicarbonate can neutralize stomach acid just because it is a weak base. But if you're thinking about Tums or Rolaids, well, Tums uses calcium carbonate to help neutralize stomach acid, whereas Rolaids just use calcium carbonate as well as magnesium hydroxide, both of which are bases, to neutralize stomach acid. For foods, there's a variety of different foods that can have a variety of different pHs. So, for example, pop, that would be more on the acidic side there. Okay, same with vinegar. It's going to be more on the acidic side. In industry, pH is important for regulating the pH of pools, which in general you want your pH of your swimming pool to be around 7 or 7 to 7.6. Okay, anything outside of that and swimming in a pool that's outside of that range of 7, a pH of 7 to 7.6 will be uncomfortable. Okay. Now, another example of the pH of substances being important would be the pH of blood. So blood typically has a pH of 7.4. And what's interesting about blood, so maybe I'll write that right there, is if the pH of your blood increases to 7.45, and if it gets any further than that or any more basic than that, you actually get a condition called alkalosis, which is not good for your organs. Your organs actually can't survive at a higher pH than that. And so what happens is your organs will eventually shut down and die because the pH is not great for them functioning. So alkalosis. And on the other side here, if your pH of your blood decreases to 7.35, and actually if it goes anywhere lower than that, you get a condition called acidosis, which means your blood is too acidic and it is too acidic for your organs to function, so they actually start to shut down and die. You can reverse these two conditions, but that's going to take some IV fluids. If you have the case of acidosis, you're going to want some more basic IV fluids, or if you have alkalosis, then you'd want more acidic IV fluids. Okay, so that's interesting there, just with your blood, that your body operates in quite a seemingly narrow range of pH. Because otherwise, if it's outside that range, bad things start happening to your body. Okay, now with acids, typically acids are molecular compounds that are going to produce H+ ions when they are dissolved in water. So this is part of that original Arrhenius definition. So I'm going to write that right here. Arrhenius definition. Okay, and as we said earlier, for acids, your pH is going to be less than 7. Acids are going to react with bases. They taste sour, although you shouldn't be tasting anything in the lab. But if you think about, if you're thinking about sour candy, right, it tastes quite sour because of an acid that's in the candy. Acids are also going to turn blue litmus paper red. And some common acids are going to be hydrochloric acid, acetic acid, carbonic acid, sulfuric acid, and then phosphoric acid. Okay, so we will be getting into how to name acids there, and also near the end of this video, I'm going to show you a video as to what blue litmus paper turning red looks like. We call it red, but it's a little bit more on the pink side. Okay, so for bases, the original Arrhenius definition of bases is just compounds that produce hydroxide ions, so OH1 minus, when they are dissolved in water. And the pH for bases is going to be above 7. They don't react with metal, they feel slippery, taste bitter. So for bases, if you've ever accidentally gotten some soap in your mouth, or maybe you intentionally put soap in your mouth, or you got soap put in your mouth by your parents, if you've ever tasted soap, it definitely tastes bitter, and obviously, like we've all felt soap, it feels quite slippery. Okay, soap is just something that is more on the basic side. Bases are also going to turn red litmus paper blue, and some examples of bases is going to be sodium hydroxide, ammonia, and sodium hydrogen carbonate. One last thing before we move on here, just to help you like easily identify acids, which we will get into. Most of the time, acids are either going to begin with H or end in COOH. So I'm going to just add that as a little note at the end here. So as you can see from all of these examples, they either begin with H or end in COOH. Okay. So that's a quick way that you can identify acids. Now, for naming acids, like we said, acids are hydrogen compounds that produce H plus ions in solution if we are talking about the original Arrhenius definition of an acid, which we will talk a little bit more about in a future lesson. Okay, so acids form ions in solution. So what that means is that they're going to ionize in solution. So they must be electrically neutral, like ionic compounds. So what this means is if you're trying to figure out how many hydrogens you should put in your chemical formula for your acid, what you need to know is that the number of hydrogen ions must balance whatever your non-metallic ion's negative charge is, which we'll get into that in a little bit here. Acids are named according to the hydrogen compound that is dissolved in water, and some acids are made up of polyatomic ions. So these, like all other acids, form ions in solutions. For our rules for naming acids, we're going to identify the acid by noticing that it begins with an H or ends in COOH, and then you need to know that all acids are soluble in water, so whenever you're writing out an acid in a chemical reaction, its state should be aqueous. So I'm just going to add in some notes here. acids begin with H or end in COOH, and then state for acids is always aqueous. So aqueous just means that the substance is dissolved in water. Okay. So what you need to be aware of is how to name acids. So what you are used to is the IUPAC naming system. Okay. However, most of the times acids are referred to using the classical naming system. So we need to be aware of both, and you need to know how to name acids using the classical naming system. So for our first example here, using the IUPAC naming system, okay, this is just involving a compound that's acidic that has hydrogen with some other element from group 17. So if we look at our periodic table, group 17, that's going to include fluorine, chlorine, bromine, iodine, and astatine. Most of the time you don't see astatine used, but the first four there are used quite commonly. Okay, but for our first item here, we're looking at compounds that have hydrogen with only one other element that's coming from group 17. So for example here, let's talk about HCl. Okay, so we would call this aqueous hydrogen chloride if we were using the IUPAC naming system. So again, we're keeping the ending as IDE like we would normally do if we're trying to represent a metal that is, or sorry, a non-metal ion. Okay. I'm also going to add in here that this is for compounds that have hydrogen with only one other element. And that one other element is usually from group 17. Alright, so that's how we would typically name a compound like HCl. We would name it aqueous hydrogen chloride. However, with the classical naming system, what that turns into is hydro, and then this is just the root word that comes from the element. So in our example, because our other element with hydrogen was chlorine, or chloride I should say, this would turn into hydrochloric acid. Okay, so I'm going to go through the rest of these, but then I'll give you a mnemonic device or a memory device to help you remember how to name acids. With the next case that we have, we're going to have hydrogen with a polyatomic ion that ends in 8. So for your polyatomic ions, those are all going to be found here. Oh. And so with the ions that end in 8, like phosphate or nitrate, or sulfate, this is going to be the rule for compounds with hydrogen and polyatomic ions that end in 8. Okay, so we would call them aqueous, hydrogen, and then this is just the root word from the polyatomic ion ending in 8. So you don't change the ending for the IUPAC naming system. So for example, let's say we have HNO3, which is aqueous, and I should have wrote aqueous for that for hydrochloric acid above. But using the IUPAC naming system, we would call this aqueous hydrogen nitrate. Now, if we switch over to the classical naming system, what that name would turn into would be nitric acid. So again, this right here is just representing like the root word coming from the polyatomic ion, but it's always going to end in ic acid if your polyatomic ion name ends in 8 or ATE. Okay. Last but not least, if we have a polyatomic ion that's name ends in ite, ITE, then we're going to have yet another rule for that. Okay, so some examples of polyatomic ions that end in ite would be sulfite and nitrite. There's more than that, like chlorite there, but that's just going to be the few that I mentioned. So let's say, for example, we have HNO2. So it looks pretty similar to our previous example. However, our previous example used nitrate, and now we are using nitrite. Okay, so using IUPAC naming rules, we would call this, I should write that as aqueous, aqueous hydrogen nitrate. Now, if we converted that into the classical naming system, that would change into nitrous acid. So essentially what this is saying is if you have a polyatomic ion whose name ends in ite, your acid name is going to end in us acid. Okay, so how you can distinguish this first case that we had where we were naming our acid hydro and then root word coming from the element and then ic acid versus these two here is this first case you're only going to have hydrogen with one other element, but with these other two you're going to have hydrogen with more than one other element. And if you have hydrogen with more than one other element, you are not going to put hydro in front of the name. So like notice that in these last two cases we did not write hydro. So when hydrogen is with more than one other element, you don't need hydro, or you don't need the word hydro in your name. Okay, so how are we going to remember how to use this classical naming system? Okay, so I'm going to have to squeeze in my little trick. We'll have to squeeze it in the middle here. Okay, and what I'm going to have to do is I'm going to label this A, B, and C. Okay, so for the case of A, the sentence that I use to help me remember how to name the acid using the classical naming system would be, my ride has hydraulics, which I'm going to have to scooch to the next line. So what this is saying is, if in the original name it ends in IDE, you're going to have to start the acid name with hydro and then end it with ic. So let's write that out, what I just said. Actually, I'm going to have to move this down. So the acid name starts with hydro and ends with ic. And then we're just assuming that you know to also add acid. So be aware of that. For case B, so that's when we have hydrogen with a polyatomic ion that ends in 8. The sentence that I use to help me remember how to name acids with that case is this: I ate something icky. So if it ends in 8, then you need to change the ending of the name to ic and then obviously add acid. Okay. And you know what? I'm just going to add the acid in. So ic, and then I'm going to also add it to the other part here, ic acid. And then for the last case here, this is when we have hydrogen with a polyatomic ion whose name ends in ite. So this is case C. And the sentence I use to help me remember this case, whether you agree with this or not is irrelevant, but Sprite is delicious. So essentially what this is saying is, if you see a polyatomic ion whose ending ends in ite, then you're going to change the ending of the name to us and then add acid. So this is how you can memorize how to name acids using the classical naming system. Okay. So be aware that you're going to have to be able to convert from name to chemical formula and vice versa. Okay. So with this one, we've already done hydrochloric acid. So let's just switch this up. Let's change this to hydrobromic acid. Okay, so hydro, that means that it's hydrogen with only one other element. Okay, so I have H, and then brom. Well, what kind of element does that sound like? If we go to our periodic table, we know that hydrogen with only one other element, the element usually comes from group 17. And brom from bromic sounds a whole lot like bromine. So then this is just HBr. Now, hydrogen likes to have a +1 charge. And you can see that if you go to your periodic table, check out hydrogen. It does say either a +1 or a -1. A -1 is a hydride, which we are not talking about. We are talking about hydrogen with a 1+ charge. Okay, now for bromide, since it's part of group 17 ions like to have a -1 charge. So bromide is going to have a -1 charge. And since the +1 and the -1, those charges balance out, we don't need to worry about any subscripts. So we're good on that. All right, I'm going to do this one down below here, and then I'll move on to the other side. So we have H2SO4. So I'm noticing that we have hydrogen with more than one other element. So that means that we're going to use one of the last two cases. So either case B or case C. Okay. So what we need to do is be like, okay, what is this polyatomic ion called? So if we go to our periodic table, find the list of polyatomic ions, we can find this ion right here, and it's called sulfate. So if it ends in H, then you need to remember I ate something icky. So we're going to change the ending of the name to ic acid. So let's write this out, sulfate. Now with this, it's not going to be perfect, so we are going to change the ending 8 to ic. However, you'll need to be aware that it's actually sulfuric acid. So just be aware of it. Like these rules aren't perfect, but with time and with practice, you'll get used to little anomalies like this. Okay, so we're changing the ending 8 to ic acid, but just with this compound here, we do have to call it sulfuric acid instead of sulfic acid, which is what one would expect given our rules. Okay, so moving on here, we have H3BO3. So we have hydrogen with more than one other element in it. So I know this is going to be a polyatomic ion. So let's check this out and see where it is here. So this looks like it's right here. So we have borate. So with this, so borate, we end with 8, so we need to change it to ic acid. So boric acid. Okay, so this is the name. This is just my background work behind the name, just so you can see how I'm arriving at the acid name here. Okay, with nitrous acid, so we're going to be creating the chemical formula here. So us, that tells me that my polyatomic ion ends in ite. And so to figure out like the root of nitrous, right, I'm looking for something that has nitrite in it. Okay, so I'm just taking this part and kind of reverse engineering what the polyatomic ion name is. Okay, so with this, nitrite, that's NO2. So we would go H NO2. Now, NO2 likes to have a -1 charge. Hydrogen likes to have a +1 charge when it's an ion. So these charges balance out, so it's all good. All right, now with naming bases, it's less complicated to name bases because you don't need to know like a new naming system in order to name bases. Bases just follow the IUPAC naming system. Okay, so it's saying here you can easily identify a base if you see a hydroxide group in it. Okay, so if you see a metal with hydroxide, that's going to tell you that you have a very strong base. Okay, so we use IUPAC rules for naming ionic compounds. So these are typically identified with a metal with hydroxide, which is just OH1 minus. So if we look at our example, we have calcium, which is a metal, with hydroxide ions. So remember that ionic compounds don't use prefixes when you are naming compounds. So with this, we're just saying, okay, this is our metal ion, so calcium, and then hydroxide. So we don't need to say dihydroxide to represent that there's two of them. Okay, and the reason being is because for ionic compounds, since it's a cation, which is a positive ion, and an anion together, you can use that to figure out how much of each you should have, because you should know that you're always trying to create a neutral compound. Okay, so I'll just demonstrate here with this next example, barium hydroxide. So barium, that's a metal. Hydroxide, that's a hydroxide group we're looking at to tell us that, yep, we have a base. So barium, that symbol is Ba. And then we have hydroxide. Now, for the charges here, if I look at my periodic table, and if I find barium, I'm finding it right here in group 2. Now, a reminder that group 2 ions, they're going to like to have a 2+ charge. So, barium likes to have a 2+ charge. We know hydroxide likes to have a 1- charge. If you wanted to know where to look that up for hydroxide in your periodic table, you just go to the list of polyatomic ions, and then you would find hydroxide, which is right here. Okay, so you can see he got that -1 charge. All right, so since we know that 2 minus 1 does not equal 0, we got to do crisscross applesauce. And since I need to pull this 2 and put it behind the hydroxide here, I need to represent that there's 2 hydroxide ions, so I need to put it in brackets. Okay, so now that we've done crisscross applesauce, I'm not going to write the 1 behind barium because it's already assumed if there's nothing written there that there's 1 barium ion. And that's all good. With this next one here, so Na, that's a symbol for sodium. And then we have hydroxide. And then last one, zinc hydroxide. So zinc, if we check that one out, that's going to be right here. So zinc likes to have a 2+ charge. So zinc, and then we had hydroxide. So zinc likes to have a 2+ charge. Hydroxide is -1. We gotta go crisscross applesauce because we know 2 minus 1 is not 0. So we're bringing this number down behind the hydroxide so that the compound balances out so that it's a neutral compound. Alrighty. Moving on to neutralization. So neutralization is just a name for a reaction that occurs between an acid and a base. And a neutralization reaction always produces some sort of salt and water. And what we mean by salt is that it's some sort of neutral ionic compound. So for example, if we have stomach acid reacting with some sort of antacid, so for example, Tums, so HCl, hydrochloric acid, that's representing our stomach acid, and sodium hydroxide is representing Tums. So when those react together, it's going to be called a neutralization reaction, and this is our salt, so it's a neutral ionic compound, and then we also have water being produced. So this is a specific double replacement reaction that is called a neutralization reaction. Okay, so you should be aware that a neutralization reaction just occurs between an acid and a base, and it produces salt and water. All right, so here's a table that summarizes all of the solutions that you should be aware of. Okay, and it has the theoretical definitions as well as the empirical definitions. Okay, so theoretical definitions just kind of explain how we would expect or what we would expect the compound to be made up of. Okay, whereas empirical definitions are derived from, like, this is how we would expect this compound to act, or how we would expect to be able to use our five senses to determine this compound. So non-electrolyte versus electrolyte, we'd be able to determine that by looking at a conductivity apparatus and seeing how it's operating. When it's talking about litmus paper, we're using our sense of sight to be like, okay, is the litmus paper turning red or blue? Okay, so just going through these definitions. For neutral molecular compounds, these are solutions of compounds that are composed of nonmetals only. These compounds are not acid or base forming. Why? Because they're neutral. Now, we are going to have to adjust the notes here. So because it's a molecular compound, we cannot say that it dissociates because that's specifically for ionic compounds, but we can say that it does not ionize. Do not ionize into ions. Okay, so what that means is this compound will not break apart into its ions when being put in water. Okay, so some examples of neutral molecular compounds would be something like sucrose, or down here, this would be called methanol. So these are two neutral molecular compounds here. For the empirical definition, neutral molecular compounds, they are going to be non-electrolytes. They have no effect on litmus. They have a pH of 7 because they are neutral. And typically, they're going to form colorless solutions. Okay. Let's also highlight this because that's actually pretty important. For neutral ionic compounds, those are going to be solutions of compounds that are composed of metals combined with nonmetals. These compounds are not acid or base forming, again, because it's neutral ionic. And if they are soluble in water, they do dissociate into ions. So let's just add that in. If soluble in water. So how you know if something's soluble in water, if it's an ionic compound, is you need to check your solubility table, which is right here on page 6 of your data booklet. So some examples of neutral ionic compounds would be sodium chloride, and calcium bromide. So again, if they are soluble in water, neutral ionic compounds will be electrolytic and they will have no effect on litmus paper. So the whole point about litmus paper is to tell you if a solution is acidic or basic, and if it doesn't change, like if neither the blue litmus paper or red litmus paper changes color, so it has no effect, then that tells you that your solution is neutral. Okay. And as a quick reminder here, non-electrolyte versus electrolyte, what that means is non-electrolyte means no ions are present. Whereas electrolyte means that ions are present. For neutral ionic compounds, they are going to have a pH of 7 and form colorless as well as colorful solutions, depending on the ions. For acids, these are going to be solutions of compounds that produce hydrogen ions, and they are going to ionize into ions because typically these are going to be molecular compounds. And how we can identify them is they begin with hydrogen or end in COOH. Okay, so for our examples, we have hydrochloric acid and sulfuric acid. So both of those begin with H. That's how you know that they are acids. Acids, they are going to be electrolytes, so ions will be present, and acids are going to turn blue litmus paper red. Red litmus paper will still stay red. The pH is going to be less than 7, and they are going to taste sour, as well as react with metals, and they neutralize bases. With bases, these are going to be, they can be ionic compounds. They can also be molecular compounds as well. Strong bases typically are ionic compounds. They are going to dissociate into ions, assuming they're soluble in water. Some examples would be potassium hydroxide or magnesium hydroxide. Assuming they are soluble in water, they will be electrolytes, and bases turn red litmus paper blue. Blue litmus paper will still remain blue. Okay, so how you can remember the difference with how litmus paper acts, you could remember like for red litmus paper turns blue for bases, well, B for blue for base. That's how I remember it. Okay, for bases, their pH is going to be above 7. They'll taste bitter, feel slippery, and they will neutralize acids. Okay. Now, right at the bottom here, it just has the definitions of what an empirical definition is and what a theoretical definition is. So again, empirical definition is just a statement in terms of observable properties. Okay, whereas theoretical definition relates to explanations and involving non-observable properties. So, as promised, I am going to show a video just with what litmus paper looks like, just so that it's not just me talking about it and you don't really understand it because you can't see it. So, here we got an experiment. And I'm just going to talk over this video as it goes. So essentially what this person's done is she's taking blue and red litmus paper, and she's got a variety of household substances which she's going to test the pH of. So here she's trying water. So as you can see here, the red and blue litmus paper, red has remained red, blue has remained blue. Therefore, that's how you can tell that water is going to be a neutral substance. Okay, and if you remember the chemical formula for water, it's H2O, so it's going to be a neutral molecular substance. Next is hot sauce. So she's dipping it in. And you can see that the blue litmus paper is turning red here, whereas the red litmus paper remains red. So this is telling us that hot sauce is an acidic substance. Now we're testing vinegar. So a bit more of a dramatic change here that you can see blue litmus paper turns red, red stays the same, so this is going to tell us that vinegar is an acid. Next we have bleach. So as you can see, blue litmus paper stays blue, but red turns blue, so B for blue for base. Bleach is a base. Next we have soap. So the soap is on the side there, she's just trying to get it. So as you can see, if this will focus, the blue litmus paper did turn a little bit red there, so this soap is slightly acidic. Next we have Sprite. So as we can see, maybe I'll back this up a little bit. The blue litmus paper did turn a little bit red, so this is going to be acidic. Next we have glass cleaner. Red litmus paper turned blue, B for blue for base. Glass cleaner is a base. We have orange juice now. So as you can see, blue litmus paper is turning a little bit red, so this is a little bit acidic. Now we have cleaner. So red litmus paper turns blue, B for blue for base. Cleaner, this cleaner is a base. Last but not least, we have milk. And it doesn't look like there's much of a change, so blue litmus paper stays blue, red litmus paper stays red, so it looks like milk is a neutral or close to neutral substance there.